please to have energy to listen a little bit about X-ray emission spectroscopy and not about diffraction. So the motivation of this talk is we have recently commissioned a prototype in-house built X-ray emission spectrometer. So the experiment instrument is almost ready for the users. We haven't given it. So I will go through in the next 30 minutes. I'll go through the design and construction and how it works. So this is my overview of my talk. I'll talk a little bit about the X-ray emission spectroscopy, a brief introduction, and then I will compare the XES with the XAS, which is very well known. Most of the people are familiar with the XAS. And then I will talk about the spectrometers that are being traditionally used for XES measurements. And then I will talk about our miniXES, then the XES measurement, and then finally a little bit about the calibration and data analysis procedure. So with that, I will talk about what is emissions, X-ray emission spectroscopy. So what happens is when X-rays with sufficient energy interact with an atom, what happens, the most possible thing is that a core electron gets removed. When the core electron gets removed, the atom is now in the excited state. This excited state is very short-lived, order of femtoseconds. So what happens is the system, since the system is in excited state, the electron from the higher orbit sees an opportunity to move to the lower state, so it moves and fills the core hole. So, but now the system is in lower state, the ground state, but the energy is not conserved. So therefore, what happens? The X-ray is emitted, and the X-ray energy is the difference between the higher shell and the lower ground state. And since the emitted energy is characteristics of that particular energy levels, the difference between these two energy levels, those are unique to each of the atoms that we are looking at. So this is a photon in, photon out technique. So at the same time, there is a complementary process. This is when the photon are emitted, this can also knock out an outer shell electron. Those electron is called OJ electron, and studying about OJ electron is called OJ electron spectroscopy. So in this talk, we will be mainly focusing on XES. And just to remind, the OJ electron is called the photon in and electron out spectroscopy. So now there are multiple transitions possible, because when the outer shell, it can, from L, M, N shell, it can go to the core level. So we will see what kind of transitions can happen. So I have put a schematic diagram here. There are multiple transitions possible, but this transition has to follow certain selection rules. So the transition that follow the selection rules are the most probable transitions, but it does not mean that the other transition can't happen. For example, this transition from level L shell to the N K shell is called K alpha, M shell to the K shell is called K beta transition, and so on. Then, for example, if it is from you can see, so the L alpha, L beta, and from the higher shells to the L shell. So here also I have listed. So the selection rules are the energy has to be conserved, and the dipole selection rule has to follow between the initial and final state, which is the delta L is equal to plus or minus 1, the orbital angular momentum quantum number. And the same as angular, total angular momentum has to be plus or minus 0 or plus or minus 1. So if these selection rules are satisfied, then the many transition can happen. Then the next, so here this is a typical X-ray emission spectra of a 3D transition methods or lanthanides. So here you can see the K alpha and K beta is well separated by, for example, for iron, it's separated by about 700 eV. So any spectra, any detector which is capable of giving 100 to 150 eV resolution, that can easily detect or resolve the K alpha and K beta lines. For example, such as like a silicon detectors or germanium can easily resolve these K alpha and K beta. But when you look at closely, the K alpha lines are now separated into two. This is because the spin orbit interaction or the LS coupling. So these lines are separated now. This separation is about 10 eV. But if you look at the K beta lines, the K beta lines have even smaller splittings, And this is due to the electron-electron interaction. The process is like a shake-up, shake-off, and this will also give the satellite lights. And just want to mention this K-beta 2,5 lines. This is for the dipole selection rule, does not obey this one, K-beta, because it's 3D to 1s transition. But it's the electric quarter pole moment selection rules will obey for this one. So that's why this K-beta transitions are K-beta 2,5 transition is very weak. It's almost 1,000 times lower than the K-alpha weak. So in order to measure this K-beta transitions, we need to have a resolution of the spectrum. The spectrometer resolution has to be very fine, around 1 EB or less. So with that, so before going to the spectrometer, I just want to compare how this XES compare with the X-ray absorption spectroscopy techniques. So as we know, the X-ray absorption is a primary process because the X-ray absorption happens first. So the electron gets knocked out, so that's why it's called the primary process. The X-ray emission happens after the absorption, so it's called the secondary process. Also, in X-ray absorption, the electron is moving to the continuum, so it mostly explores the unoccupied states. Whereas in the XES, it's the electron transition to the occupied levels. Therefore, this can be explored by the density of states of occupied states. And now, as you all know, XAS is divided into two, SANES and XFs. So SANES can know the coordination, it can measure oxidation state, coordination number, and so on. The same thing, XFs, for example, here, the SANES is close to the absorption edge, and XFs follows the absorption edge, like what we see is like a ripples. That can give information about the bond angle and distance of neighboring atoms. And then in XES, for example, K alpha, this line is normally used for reference. It's very sharp peak. And K beta has K beta prime and K beta 1,3. These two states are very sensitive to spin. So high spin, low spin. If there is a high spin to low spin, then there is a shift in the energy, then we can easily find out. And also the oxidant, if the oxidant state is different, then the peak will be shifted. So you can easily find out if there is any oxidation state changes. And K beta 2,5 and K beta prime, those are very weak transitions. And that since these are very sensitive to the spin as well, and also the chemical environment. So mostly we will be focusing on to this K beta 2,5 transitions. That's very important to understand about the chemical environment. So as you can see, so this is also called the valence to polar transition. The next. Okay. So there are multiple types of spectrometers are used in around the synchrotrons. So I'll be talking only about two types of majorly used spectrometers. So one is called the spherically bent crystal analyzer. So as the name suggests, it has a spherically bent crystal, and this crystal and the sample and detector is all in one circle. So it's called the Rowland circle geometry. So if you want to scan the energy, for example, then the sample, the detector and the analyzer crystal has to be moved along the circle. So this also is called the focus geometry because the spherical crystal focus the X-rays onto the detector. So since it is focusing, we don't need to worry about the beam size. Even the beam size is bigger. This can give a very nice resolution. The next one is the cylindrical bent crystal analyzers. So here, instead of the spherically bent crystal, they use a cylindrically bent crystal. And then there's a sample, and here we need to use a position sensitive detector. The reason is the cylindrical crystal is along the surface of the cylinder, and the sample and position sensitive detectors are along the cylindrical axis, parallel to the cylindrical axis. So when the X-rays fall into the cylindrical bent crystal, that will be dispersed onto the position sensitive detector in one dimension. So CBCA will be a one-shot experiment. Just take one measurement. then you get the whole XES spectra. Instead, we need to, here this both have to be moved. So this is a little bit more complicated when you do the measurements. And this one is called the Van-Homas geometry, and also called the dispersive geometry, because it's the X-rays are dispersed onto the position sensitive detector, where here is focused onto the detector. So these are the X-ray emission spectrometers around the different facilities. As you can see, these are all very huge, dedicated to particular beam lines, expensive to build, and it's capable of 1 EV resolution, obviously. And then we cannot move from one beam line to another beam line. And then the working distance, for example, the working distance would mean the sample to analyzed crystal distance is about 1 meter. So it's a huge. So this is the one in diamond and the DC and the spring 8. These are also, some of them are spherical, and the last one is the cylindrical laser. So in the last 10 years or so, there has been alternate way to approach the same kind of resolution, but with a compact. So a compact spectrometer, so that we can easily put it on any beam lines and measure. So this is what the short working distance emission spectrometers. So this is almost based on the cylindrical bend crystal geometry. The difference is the cylindrical spin crystal is replaced by multiple flat crystals. And then the another difference is the crystal, we need to choose a crystal which almost backscatter. So close to the Bragg angle has to be between 75 to 85 degrees. So then what happens when you do this one, then the geometry becomes very compact. Instead of 1 meter, this will become like a few tens of centimeters. So I have put a comparison. So the traditional spectrometers are not portable. The miniXES is very easy to move, and cost-wise, traditional spectrometers are expensive, and miniXES is very affordable. It's 3D printed or even a small metal, make it in aluminum. And the working distance is very huge, and this will be about tens of centimeters. And the resolution is SPCA can give a very nice resolution, better than even miniXES. And miniXES is about 1 EV, almost comparable. And ease of use, this is each time, for example, somebody wants to measure a different element, then they need to change the crystal. That will be time-taking process. The crystal and then align. And in miniatures, it's pretty simple. The crystal holder can be removed and put a different crystal, then it's ready to go. The energy range can be slightly broader than this one. And alignment calibration is definitely complicated. And one thing, this one, miniatures, in another condition is we need to have as small beam as possible to get a better resolution. So the beam spot has to be in ideal conditions, it should be less than 50 microns to get a better resolution. Also, in the area detector, it has to have a pixel size better. So these two conditions are needed to get a better resolution in XES spectra. So this is how miniatures works. This is one of the primitive design they made. So here the crystal, this is the first one, is just a single crystal, and source, the X-rays fall onto the crystal and diffracted back to the closed Bragg geometry, and the position sensitive detector is here. So when you add multiple crystals, this is where it looks like. So there will be some overlap between each of the X-rays scattered. That's why they use a aperture in between. So this is the actual detector, this spectrometer. The source is here, crystal. The X-rays fall on the crystal and diffracted back to the position sensitive detector. And there are no moving parts, just a one-shot experiment. So this is the important thing is we need to choose a crystal that back diffract. So this is the crystal holder. This is one of our assembly. So here we will be focusing on iron. So the emission lines we are interested in is K-beta 25 or K-beta prime, double prime, and the energy range is 7,000 to 7,140. So the crystal is ideal for this energy range is germanium 620. This can easily find out. There it's a link, the diamond light source. You can choose the energy range and choose the element and the peaks you're interested in, and then it will give the possible analyzer crystals. So you can choose a crystal based on your spectrometer geometry. So the detector we are using is the Pilatus 100K, and its pixel size is about 172 microns. The size is about 83 by 33.5 millimeters. So this is the miniXES, the 3D model. So there's a back view and there's a front view. So this consists of 4 different parts. One is the Pilatus detector, and this is the lower chamber, and then upper chamber, and then motorized stages to move along the beam direction and perpendicular to that. And there is also a pitch stage to move the beam to align fine tuning. And there are 2 alignment posts. So the X-ray coming in, going through these 2 posts means the spectrometer is almost aligned. And then you put the sample here and another XYZ stage. There's a window, the crystal is placed here. You can see in this picture, the crystal is here. So this is a lower chamber where the crystal is almost like a lower chamber crystal holder. And that's the upper chamber. And these 2 chambers are connected with an O-ring, and the helium is flowed through the chamber to reduce the air scattering. And this one is the front view. The Pilatus aperture here, like I said, the O-ring, the top chamber, the lower chamber, the crystal holder, and the sample is placed here. So the X-rays come in, and the scattered, the emitted X-rays fall on the crystal and reflected back to the detector. So here you can see the X-rays comes in and falls on the sample, and the X-rays are in the crystal and then falls back. So this is the back geometry. So this is the XES measurement. So we use undulator beamline. So the sample selected, these are reference samples. So the FP203 and the FP304. The sample is sandwiched between some Kapton tape and mounted it on the XYZ stage. And the beamline, this undulator beamline, as equipped with 2 monochromators, one a multi-layer monochromator, and then as a channel cut. And then the beam is focused with a KB mirror. The beam can be ideally focused to 20 micron vertical and 170 micron horizontal. But currently we have issues with the KB mirror, so that we are getting around 150 to 200 microns. And the beamline can go up to 5 to 24 keV, and the flux extends to about 12 to 13. So this is the actual setup at the beamline. So this is a Huber diffractometer, and upstream the beam coming from this way, and the Huber diffractometer we mounted on an optical table. So the sample is placed on this XY stage, the Pilatus, and then the beam is going through this way. The alignment post out here, and the bottom stages are to align the spectrometer. And also, I forgot to tell you this. The main technique in the BXDS undulator beamlines are mostly X-ray diffraction, reciprocal mapping, and grazing incidence diffraction, mostly reflectivity, and then magnetic diffraction. Also, wax SAS can also be done. And we do have as I mentioned, a 6-axis Huber diffractometer, and we have a rayonics detector that can give about 70 microns resolution, or 30 centimeter by 30 centimeter, and then the lambda detector, which is 55 microns, and the flatter detectors that we are using here is about 170 microns. And we do have a cryostat and a vortex detector and also a polarimeter. So with that, next one. So this is the actual setup. So we have lots of lead tape and copper shielding around to reduce the air scattering. This show. And this, so as I mentioned, the powder samples are between the Kapton tapes. So this is the image from the Fe203, just a single shot. The beamline is tuned at 7900 eV. It's well above the absorption edge of iron. And this is from Fe304. So when you take a region of interest from using an image or any of the software, just it will plot the K beta 13, K beta 25, and K beta dash. And then when I take a log plot, then you can see even the K beta 25, which is very, very weak, the forbidden transition. So we can still resolve but the background is still high. The next I will be. So as you can see here in this plot, the x-axis is still not the energy scale; it's a pixel size pixel. So we need to do a calibration to make to assign each pixel of the detector an energy value so that we can get the spectra with the energy at the x-axis. So to do the energy calibration, what we have to do is we need to tune the beamline to the range of the spectrometer from starting from 7,000 to 7,150. So we take snapshots at each energy, about 15, like 10 eV difference, like 15 images. We can also take even 5 eV steps. Only things we need to tune the beam 7,000 and then take a snapshot. And then as you go up to 7,150, so you'll finally end up with having 15 images. So as you can see, the 7,020 and 7,040, the reflections keep moving down as the energy is different. So once you have the energy, so we can easily do the calibration. So to do the calibration and analysis, I have used, there are multiple softwares available. So I have used one of the Argon X-ray emission analysis package. This is a MATLAB-based software. It's easy to operate. So this is a screenshot of the AXCP software. So here I have uploaded all the 15 images. So basically only 13 of them because the top and bottom one is outside the detector area. So once you have uploaded all of them, so you select a region of interest. So the region of interest is selected. Then what it does is initially we need to do a fitting. So they will fit because we have only 13 energies, we need to fit to the whole range from 7,000 to 7,130. So once the fitting is done, then it will be, we need to calibrate. So once we calibrate, that means it will generate a calibration energy map, which means that the energy values of the detector, energy values assigned to each pixel of the detector. So you get a calibration map. And then once you have a calibration map, we upload the actual image and to extract the final spectra. So this is how we select the multiple ROIs. Sometimes we see hotspots you can exclude. You can also not see the last crystal only partially visible. You can exclude. You can select as many as you want to degrade the signal. So once you have selected, then you do a calibration. Then something like this will get the calibration energy map. So we can also find out the resolution. These are the elastic peaks from each of the crystal shot. So by fitting each of these peaks, you can get the resolution. For some reason, the program, I could not run the resolution part. It's not working, but I manually calculated. It's all less than every EV. And then once you have, then you can extract the XEX spectra. That's what it looks like. So you take as many as our region of interest you want, and then it will be fitted to the actual image. Then you get the final spectra. So this is the from one of the reference from APS. So this is our spectra. It's pretty looks identical, but the K beta 2.5 peak is they multiplied by almost 40. For example, here I had to multiply almost about 500 times. Even then, it's not very solvable. But the reason being, their beam size is about less than 30 microns. Our beam size is around 200 microns, 150 to 200. So if we make the beam size smaller and then reduce the air scattering a little bit better, then we'll be able to resolve exactly like the same way. So I have given a couple of, there are other miniatures available in other facilities. So I have listed a couple of them, just in case if you're interested in. So I'll close with one just example that the similar things can be used in our miniatures. So this is something about the nitrogen fixation. So we all know this nitrogen is an enzyme that is very important in transforming nitrogen from air into ammonia so that the plants can easily utilize. So this nitrogen is something that looks like this. So the main constant of this nitrogen is called the iron molybdenum cofactor, which is a small cluster which is responsible for the transformation. So, but the research have been trying to understand the structure, and the main concern is the central atom of the cluster. So the problem is the central atom. This lithium molybdenum cofactor is made up of 7 ions and 9 sulfur and 1 molybdenum on one central atom. The central atom is a very lighter atom surrounded by heavier atoms. Therefore, the traditional spectroscopy techniques could not identify. So they used the miniXES, and there's also suspicion that the central atom could be either carbon, nitrogen, or oxygen, and the whole thing surrounded by the Cartesian wave. So it is very difficult to identify the central part of the central atom. So they used the XES to measure the K beta 2pi and K beta prime. This looks like. So these are, one of them is a complete APM co. They have a iron molybdenum cofactor, and one of them is the whole nitrogenous, and then the last one is the isolated, the protein part is removed. So they can see wherever this iron molybdenum cofactor is involved, there they can see a peak. And they did DFT calculations to see the carbon has a similar peak at 7100, which matches with the iron molybdenum cofactor, and the rest all will be shifted. For nitrogen and oxygen, it should be appearing at 7096 and 7091. This way, they confirmed that the central atom is carbon. So the long-standing mystery was solved using the XES spectroscopy. So then it was done. So we tested the portable miniatures. It's working. It's very compact. The data collection is very simple, and you can convert the 2D images to 1D image. It's very easily and easily adaptable to other elements. If you want to measure cobalt or cerium, you can easily only change the crystal. And then we can use different environments, like we can use diamond anvil cell or heating, can be easily adapted to the miniXES. Also, we can easily modify the design because it's all 3D printed. And then if you want to improve further, once we finalize the design, we can make it in metal, and it will be even more better. With that, yeah. So if you want to read further, there are a couple of review articles we can.
Thank you. Any questions for Narayan?
Well,
Yes,
maybe
please.
perhaps a suggestion. You were saying that you were having problems with some of the 3D printed material because of warpage.
Yes, yeah.
It could be useful to switch to a different plastic
I think
to prevent warpage.
so. Now we have a better 3D printer, which gives probably a better printing. We have tested.
You can also anneal plastic. I didn't realize it's semi-crystalline, and that can get rid of the strain in it that can prevent its warpage. So
I think the ones which we are using, the new printer, we're using a different material, which are much better than the.
better.
Any other questions? If not, the last chance. Okay, let's thank our speaker again.